I'll go through them if they are available. Maybe tomorrow, if the class is there, then I'll send you tomorrow. Otherwise, I'll mail you back.
Okay, ma'am.
Yes. So today we'll just wrap up and maybe we'll go through all the revision. We'll go through the revision thing, whatever we have done, so that it will be clear to you. Should we revise or should we go ahead?
Week 8, ma'am. Will we go with a week 8?
Week 8. Okay. Actually, week 7 is pending. So we'll go with the week 7 and then we'll revise, and some of the things of the week 8 we'll cover tomorrow and then we'll complete that. Is it fine?
Okay, ma'am.
Because I got the mail, maybe they are seeing offline for the revision and all.
Ma'am, sorry to disturb again, ma'am. I have one more doubt, ma'am.
Yes, yes.
Ma'am, is there any negative marking for the exam?
That also I think you should mail. I have no idea about that. You are
Okay.
given the instructions about that, the exam and all. Is there written the negative marking or is it not written?
The instructions
Maybe
will be sent in mail, ma'am.
send them mail or otherwise I'll confirm and I'll mail you back.
Okay, ma'am.
So last time, just for an overview, then I'll go ahead. Only for the last, just the overview of that. We did the martingale as well as the absorbing and transient state. And you attended the last lecture or you missed that?
I missed, ma'am. I only know up to Markov chains, ma'am.
Okay, okay. Actually, there was a doubt in the question. Like there are two Markov chains. Many of the people were having the doubt. Maybe it's an assignment problem. Let's see that. Assignment 6 problem. Can you open that?
Yes, ma'am.
I will open up.
Which question, ma'am?
Wait a second. I'm opening about the absorbing Markov chain. I have uploaded the videos as well. I think the Google Sheet is also shared with you. You can see the previous videos also.
Okay,
Question
ma'am.
number. So in question number 4, can you tell me how it is like absorbing state? You know about absorbing or transient state, or we can discuss. Any idea?
Ma'am, I think if it comes back to itself, a state, if it comes back to itself, it is a absorbing state, ma'am.
Hmm. Absorbing state is if I'm going to any state, I can, like, suppose I'm going to E here. I'll never go back to any other state. This is basically trapping or absorbing means I came to E. Now there is no way of going back to any other state. That is basically an absorbing state. So now,
Oh, okay.
okay, and the other states which can go to the other states as well, they are basically transient states. So Markov chain is divided into absorbing state as well as transient state. So last time we were having a confusion in this. So let's see these two diagrams. So which one is the absorbing Markov chain? Now if we see the first diagram here, what do you think? Is there an absorbing state here?
Yes, ma'am.
Which one?
For A, ma'am, it is not going back from any direction, so it is absorbing.
And what about E?
E, 1 minute. No, ma'am, E is not absorbing in the second diagram because from E, two states are going from to D and C.
What
So
about first diagram?
first diagram is absorbing, ma'am, because
How
from
first?
E,
Hmm.
no
Hmm.
states are going to D and C.
Okay. So first diagram, I can say A and D are absorbing states, and first diagram is absorbing Markov chain.
Yes, ma'am.
So what about this one? A second diagram, A is absorbing state, as you said. So
Yes,
is
ma'am.
this second diagram also absorbing Markov chain?
No, ma'am. I think at least two should be absorbing. No, ma'am. Two
No.
states.
Okay, okay, I'll tell you. It's not like that. Two should be absorbing. It's like that. Suppose, like, is there a path from E to A? Can I go from E to A in
No.
second chain?
Yes, ma'am. Yes, ma'am.
How? Can you tell me in Markov chain second how I'm going from E to A? Where is the path?
E to D or E to C
E to
to
A.
D,
Yes, yes. E to D. Okay.
D to B, B to A.
Is there a path from D to B? See the arrows carefully.
No, ma'am.
So, is there a path from E to A?
It is not there, ma'am.
Is there a path from D to A?
No, ma'am.
Is there a path from C to A?
No, ma'am.
So basically, a Markov chain is like absorbing if I can go, if it is possible to go from any state, like I am going from any state like A, B, sorry, C, D, E, and then reaching to the absorbing state. Basically, from any state, we should reach the absorbing state itself. Like from E also, I have to reach the absorbing state. That is then only I can say that this is an absorbing Markov chain. From C, I should reach A. From D, I should reach A. But I can't reach A. I can't reach the absorbing state basically. So that is why it is not an absorbing Markov chain. It is not possible to go from any state to absorbing state. That is why it is not an absorbing Markov chain. You got the idea?
Ma'am, how is one different then, ma'am?
Actually, students were also having the doubt here. Now I have two absorbing states, A and E. Okay. Now, can you tell me like what are the transient states B, D, and C?
Yes, ma'am.
Now, can B, D, C reach E? B, D, and C reach E?
Yes, ma'am.
So, can I say that this is absorbing Markov chain because all the transient states are reaching one absorbing state at least? A itself is absorbing state, but it is not reachable. But if I say B, D, C, they are transient states. All the transient states should reach the one of the absorbing state in the Markov chain. If the transient states are basically reaching one of the absorbing states, then we call it as the absorbing Markov chain.
Okay, ma'am.
Okay, is it clear?
Yes, ma'am.
Actually, students were also having the doubt like why when A is not reaching to E, how can you say that this is also an absorbing Markov chain? But A itself is not a transient state. That is why we are considering here that this is an absorbing Markov chain because all other states except the absorbing states are reaching it.
Okay, ma'am.
Okay, and so let's proceed to probabilistic methods and then we did hashing also as well in the last class. We flavored it with some data structure concepts also how the hashing is there. If I compared the hashing with the arrays, how hashing is better than arrays or why we need hashing if we are having the array to store. The reason was it is more like it will take lesser time to search. That is why we came up with the hashing concept that is like big O of one only the constant time it will take. Then we studied about collisions there and then the theorems and all. Now, coming to the next part, probabilistic method. I'll just give you the overview. I want that we should start with the revision as soon as possible so that whatever we have covered, we should go through all the concepts. So any idea about Ramsey number or graph coloring? Anyone? Yes. Okay, let's study that. Before studying that, any idea about complete undirected graph? What is complete graph? What is undirected graph? Yes, come on. So basically, a graph in which all vertices are connected with the all other vertices, that is basically a complete graph. And obviously, where the direction is not there, basically that is undirected graph. So if I say about this, so is this a complete undirected graph? As I told you, all the vertices are connected with the all other vertices. That is complete graph. What about this? Can you tell me, is it a complete undirected graph? Yes, come on. So basically, yes, we can say that it's a complete undirected graph. Sorry. Because if I say that, suppose A, B, C, these are my vertices. So I can say that A is connected to B, A is connected to C, both of the vertices. B is also connected to both of the vertices, and C is also connected to both of the vertices. Here also it's an undirected graph. And we usually like use the symbol K, and how many like vertices are there? K3 we'll say, and K2 we'll say. It is basically complete undirected graph with vertices, two vertices. Now, what is this Ramsey number, or I can say the Ramsey theorem? Then we'll come with the Ramsey number basically. So what does it say? That suppose I have K6. K6 means 6 vertices and all are connected with each other basically. K and this symbol basically refers to as complete graph. I'm talking to all vertices are connected to all other vertices as well. So how you color edges of K6? I have a graph of 6 vertices. How I'll color using two colors so that you will always find monochromatic triangle. For making it easy, that is why I am using an example here. So what do you mean by, now we have studied what is complete graph? Anyone, any doubt about complete graph? Can someone explain so that I can get to know that you have understood what is complete graph?
Each corner of the each vertex is connected to every other vertex of the graph.
Yes. Yes. Now, can someone tell me what is monochromatic triangle? Anything? What do you think? Monochromatic means, mono means one, basically of one color only. So what I'm saying is, I have suppose K6, the 6 vertices here, they are basically connected with each other using two colors, suppose red and blue. Let us take. Now we have to find a monochromatic triangle. Basically, what do you mean? That set of three vertices connected by edge of same color. So basically I have 6 vertices here and 3 of them should be like connected. I'll wait a second. So basically I have 6, basically all are connected with each other, but 3 of them should be connected by a same color here. That is basically what it means. So between this K6, there should at least exist a monochromatic triangle. That is what they're trying to say. If I say that, okay, now, which means that I can say that, in other words, we want K6, or I can say K6 with the 3 vertices, either it should be red or either it should be blue if I'm using the 2 colors here. So either 3 of them should be connected by red color, either 3 of them should be connected by a blue color, then only I can say that it is a monochromatic triangle. That is what is basically Ramsey theorem. That monochromatic complete subgraph should be there. That either K3 should be red in color or either K3 should be blue in color. Or if I generalize, I can say, rather than saying K6 or something, I can say we want Kn to either have red or blue of any color. Basically, either all should be red or either all should be blue. Smallest such n, basically, that will be called as Ramsey number. Let's study this. What is this? What does it mean? Let's see. If I say R6 was there, and I say that yes, there is basically the 3 of them. Basically, they are basically either 3 of them will be red or either 3 of them will be blue here. So there is a chance that 3 can be red and 3 can be blue. So this is basically the minimum or the smallest such n. Basically, this is basically called as Ramsey number. Now, how? Let us see. Let us see the analysis. So what we do, suppose we randomly color the edges in Kn. Basically, now we are randomly coloring the edges. And now let us estimate. I'll give you the example as well. Don't worry. What should be the probability that G has monochromatic, which means same color, KK. Now this can be KK, means this can be a triangle as well if I'm saying 3 vertices. So among the 6, I can say K4 or anything like K4, K2. I can say, sorry, R4, 2. Either 4 are red and 2 are blue, basically. Something like that. So what is the probability of having this monochromatic KK? So let us see that. For all subsets, if I say, or I'll write like this. I'll write, then we'll explain like how I'm saying that S is monochromatic, the probability is 2 over 2 power k. Any idea how I am writing this? Though I'll explain with the example. We saw that till now. Like what I mean is I have a graph, complete graph, in which I have to find a subset which is having, like suppose I say that 3 3, it like three of them are basically red in color and three of them are blue in color. So that smallest number such in is basically Ramsey number. Basically all the edges, all the vertices, they are connected by the same color. That is what we find out. Now in analysis we did okay randomly color, and now what is the probability that the subset is monochromatic? Then we wrote okay, that is 2 over 2 power k. How? Let us see with an example. Then I'll go to the next step, how we are proceeding, how we'll go to the next step, how this 2 over 2 power k. So let us consider a simple scenario. Suppose I have three vertices and or three vertices suppose. And so each of them, I can say the edges can be colored as red or blue if I have three vertices. So this edge can be colored as red, this edge can be colored as blue. So how many ways are there to color this edge basically? Can you tell me?
2 to the power side of the number of sides.
So can I say 2 power 3 are the ways basically? Is it fine? So can I say there are the 8 possible ways to color? Because two ways to color this, two ways to color this, two ways to color this, as you said 2 power side, that is absolutely fine. So 2 power 3, that is 8 possible ways. And out of this, out of all possible ways, how many of them will make subset monochromatic? Any idea? Okay, denominator means the probability means 2 power 3. How many of them will make the monochromatic out of 2 power 3?
Only two.
2. How?
All should be red or all should be blue.
Yes, absolutely correct. So only two, basically all should be red and all should be blue. Is it correct now? Is this formula making sense? I gave this example, a toy example, just to explain this formula. Is it making sense? Should we proceed?
Yes, ma'am.
Hmm. A union bound now this formula was given in a lecture. Can someone tell me how they came from the previous formula to this and by union bound, that how they came? Any idea? Okay, let's see now. So the first formula was given this one, 2 power 2k, 2 over 2 power k. We saw a toy example how we came up with this formula. Let us see a toy example how we came up with this formula as well. Let us see. Okay. So let us calculate. Suppose I have n is equal to 5, that is 5 vertices, and k is equal to 3, means k subsets I have to make, basically a triangle, monochromatic triangle. And it means that I want by there should exist at least one monochromatic triangle in this 5 vertices. That is what by union bound I mean to say. So let us see how we'll proceed. Step 1. I'll say calculate number of ways to choose k vertices from n. Basically, what I mean to say is I have k is equal to 3. I have n is equal to 5 vertices, and among them I have to make a triangle. So basically, I will choose 3 of them among the 5. So how should I do? How should I choose 3 of them among the 5, or how can I choose k among n? Any idea?
Combinations.
NCK.
Yes, both are correct. Both of you are correct. NCK or 5C3, I can say. What is 5C3? Hmm. So can I say we have 10 different subsets of 3 vertices? Basically, I can choose in 10 different ways. Coming to step 2. Probability that S is monochromatic. As we have seen, that is basically 2 over 2 power 3. Now, probability that there exists S monochromatic, I have 10, out of which of them are basically monochromatic. Now coming to the formula, does it resemble with this? Let us see. So basically, what is the I think it's 10 over 2 power 2. Basically, I can say 10 by 4. Okay, let's see this formula. Is it same? NCK, basically the formula is this. This we have already done. The main part is this 5. 2, 1 minus k is basically 3. What is 3C2? 3. Can I say it's same only? So basically we can write it as like this only. In the class, they have from the earlier formula, they came up to this, but rather than writing this, we can simply go through this things which will end up in the same formula only. That is what I want to show you. And then basically the next statement given is that if the right hand side, basically this is basically less than 1, we can say it is bad coloring. Can someone tell me what is bad coloring? What do you think? Now we did lot of coloring and all. What can be bad coloring here?
Non-monochromatic.
Yes. So basically, I can say that monochromatic are not there basically as the, or I can say in other words, I'm not going to explain the whole thing. What the main intent is basically here, like as the size, or I can say, wait a second, maybe whenever the RHS basically is less than 1 or it is very less than 1, then the chances of being monochromatic are less, or I can say that is called the bad coloring, or I can say in other words, when the size basically increases exponentially, the chances of monochromatic increases, or when it decreases basically, it is less than 1, the chances of monochromatic are less. That is what is basically the Ramsay theorem. The like I tried to explain through these toy examples, these formulas, as well as this. Any doubt in this? Should we proceed forward? And I think in the starting of the lecture, many were not there. You saw the absorbing state, that doubt in the last lecture, which was the doubt in the last lecture. Have you all seen? Or maybe we'll discuss in the last. Okay, let's proceed. The next method which was discussed in the class, the first probabilistic method was the Ramsay number. The second, which was discussed in the class, is a large cut in a graph. So what do you think? What is cut? What is defined as cut in the graph? Any idea? Yes, come on.
Mapping from A to A bar.
Okay, mapping from A to A bar. What do you mean? Can you explain further? Can I say that is there an edge from A to A bar? Is it the same as mapping to A from A to A bar? Yes.
All the edges are only from A to A bar only. It
Yes.
cannot be from A to A itself.
Yes, absolutely correct. Okay, you were there in the last class. If I'm not like you were there in the last class. So
Yes, ma'am,
we
I was there.
is your doubt cleared about the absorbing state? Like we were discussing in the assignment, and we discussed that we'll discuss in the next class the absorbing
No,
state.
ma'am, I joined late this time.
Okay. Okay, let's I'll discuss. Okay, I'll again repeat it then. So I'll just repeat in the short, though I have discussed in this class. So we discussed that why the chain 2 is basically not the absorbing, like why the chain 1 is not the like why it is absorbing chain, Markov chain. Is it correct? Can you open the assignment 6 quickly? Though we have discussed in the class, but I don't want, because it's an assignment problem, it should be missed by anyone. So, and I wanted to make this session a revision one only, and want that the next you can do by yourself. And if there were any doubts, we can discuss tomorrow. Let's quickly come. Have you all opened the question 4 of assignment 6? So what was your doubt?
Ma'am, there was not an edge from A to
Now, can you read the question again? Loudly.
A state in Markov chain is called absorbing if it is impossible to leave it. A Markov chain is absorbing if at least one absorbing state, and it is possible to go from any state to at least one of the absorbing state in a finite number of steps. Consider the following two Markov chains and shown in the diagram.
So in first, which one of them are absorbing states?
A and E.
A and E.
A and E, yes,
ma'am. A and E. Now, can you tell me, is this an absorbing Markov chain? What was your claim? Yes. Come on. Come on, come on. Yes. Am I audible?
Yes, it is saying that it is Markov chain if it is possible to go from any state to at least one of the absorbing states in finite number of steps.
So is it going to absorbing state?
Yes, it is an absorbing state.
A and E is absorbing state. So are all the transient states going to absorbing state? B, D, C are going to E.
Yes,
B, D,
Yes,
C
ma'am.
are, B, D, C are going to A.
no, only B is going to A.
Only B is.
No, ma'am.
And what about E? E, everyone
No,
is
ma'am.
going. E, everyone is going. Every transient state is going. Can I say? A and E are absorbing
Yes,
state. For being an absorbing Markov chain, I can say that other states should reach the absorbing state. Other transient states should reach the absorbing state. Is that thing clear?
Okay, ma'am. Ma'am, we
yes,
are
ma'am.
talking about only absorbing transient states.
Yes. Actually, we were in the doubt in the last class. If A is also not going to E, then how can we say that it is absorbing Markov chain? But A itself is absorbing state. But second one, it's not an absorbing Markov chain because all are not reachable to absorbing state. That is why it is not an absorbing Markov chain. Is the doubt clear?
Okay, ma'am. Okay, ma'am.
Yes, yes.
Means there should be an edge from every transient state to the absorbing state.
Yes, then we'll call it as absorbing Markov chain. For it being in absorbing state, we can say that it shouldn't go anywhere. It should be like a dead end, I can say. It is a trap state, I can say. Once it is reached there, it will not go anywhere else. Is it
Okay,
fine?
ma'am. Yes, ma'am.
So as we have done the large, we discussed about the large cut in the graph. What is the cut basically? If there is a mapping, as you told, from A to A bar, or is if there is an edge from A to A bar, not within A itself, but from A to A bar. So let's write. I'll write, and then please can someone or one of you can explain what I have written mathematically. Yes, come on.
Ma'am, G is a undirected graph in which some edge exists only between A to A bar.
So
And
basically, there is an yes, come on.
A union A bar is all collection of vertices.
Yes. So basically, there is an edge from A to its complement. I can say either U is in A and V is in A bar, or either U is in A bar and V is in, sorry, A basically. So what do you mean by max cut now? We know about cut. I say that if one of the vertices is here and the other is in the other complement and there is an edge between them, then we call it as cut basically. Now, what do you mean by max cut? Yes.
Ma'am, we want to maximize the size of.
Yes, you're not audible. Can you repeat?
Ma'am, we want to maximize the size of A and A bar.
Maximize the size of A and A bar. Can you elaborate it more? Can I say more number of edges?
Yes, ma'am, more number of edges.
Basically, there should be more number of edges between A and A bar.
Yes.
Or basically maximum number of edges. Connect vertices from opposite subset. So let's see an algorithm how we'll do from A to A bar, basically how we'll do the maximum number of edges, how they are connected. Let us see. So let us take A as an empty set. For each vertex belongs to V, add V in A with probability 1/2, return cut A. Can someone explain this algorithm in easy way? What is basically this return? Yes, come on. Come on. Come on, come on.
Ma'am, we check one by one each vertices and add it so as it satisfy the condition of cut.
Okay. Can I say that what do you mean by with probability half? You said that add each vertices as like it satisfy the condition of cut. What do you mean by with probability half?
Either it should be an A or it
Ma'am,
should be
either
an A
it should
complement.
be yes, ma'am. Either it should be in A or A complement.
Both of you are correct. Basically, either it should be in A, either it should be in A bar, basically. So it's like coin tossing, or either it should be which distribution it is. Just
Binomial.
binomial or okay. Yes. Can we say Bernoulli or binomial? What is the difference? Just a quick revision.
And Bernoulli is single event and single trial, and Bernoulli is in number of trials.
Yes. Bernoulli is single trial. If I say in one trial, I'm adding in A and I'm adding in A bar, can I say it's Bernoulli? One trial. And if I'll sum up the events, then as you said, it's binomial. Just basically connecting the dots, though it's not required. So now let's analyze it. Basically, what we are doing is we are taking each vertex now with the probability half. We are basically adding the vertex in A, and with the half we are adding into A bar basically. I'll write it, then we'll go through it. Can someone explain me the analysis of this? Now the large cut is basically the maximum, I can say, the edges which are connected from one vertex to the, like from vertices from the opposite subset, I can say. So now can someone explain me what is it written, the mathematical expression? Yes, come on.
Ma'am, X is a random variable which tells ma'am either is present, ma'am, that is edge is present or not. If it is 1 or else 0. And
Okay, what
ma'am,
do
we
you
are
mean by, wait, what do you mean by cut A is present or not? Yes, you are going correct only. Just edge is present means edge is present, I can say, from one subset to another, like this.
yes, ma'am.
So
There
it
is
is,
a link between one set to another, that is A to A bar.
yes, absolutely correct. Proceed further.
Ma'am, we are calculating the expectation of X, ma'am, and we are applying linearity of expectation, ma'am, here.
Wait a second. What
and
is linear expectation? Can you tell me? Can I say this is linearity of expectation?
Yes, ma'am.
Proceed further.
Ma'am, we are summing up the probability of edge cut belonging to cut A, ma'am, which is, ma'am, 2 times half in half. Ma'am, here we are doing, ma'am, we are taking two vertices UV and considering UV and VU both. That is, U is in A and V is in A bar, and V is in A.
Yes. Can I say this is only what we are doing? That is why we have written 2 into 1 into 1 by 2 into 1 by 2.
Yes, ma'am.
So basically U is in A, V is in A bar, or U is in A bar and V is in A. That is what it is. Like two things can happen. That is why we came up with this, which is E by 2. Is it correct?
Yes, ma'am.
So let's once revise what we have done in the large cut. So others also, if they are having any doubt, they can also understand. Basically, there exists an edge from A to A bar. That is what we are trying to say. From A subset to A bar, there is an edge. That is what we call it as cut. Now we have to say what are the maximum number of edges which are connected from one subset to the another subset. In the basically how many vertices are connected by the edges, maximum number of them from A to A bar. So we came up with an algorithm. Let us take an empty A subset, and with half probability we'll add up in A, and with half probability we'll add up in A bar. Then we said that, okay, let us take X, which is basically how many cuts are there, and XE, basically that is 1 if there exists a cut, and 0 if there is no cut. Basically, if there is an edge between two opposite subsets, there is a cut. So we will take it as, basically it is an indicator variable. Can I say that? Can I say this is an indicator variable? So basically there is an edge, and then we came up with the expectation. And how we are calculating the expectation, basically by linearity of the expectation, I can say, I can write it as like this only, and the expectation can add up like this. And if I say that U is basically like in A and V is in A bar, or the other case can also happen, U is in A bar and V is in A, basically. That is how we came up with this. Now we have done today the Ramsey theorem, Ramsey number. Basically, I came up with the easy examples to understand how we are coming up with these equations there as well. And now then we came up with the other probabilistic approach, large cut in the graph, and then the sum free subset. Now, the other probabilistic approach is sum-free subset. Anyone, can you explain what is sum-free subset? Yes, come on.
Sum of any two elements in the set is not present in the set.
Can you give me an example? You said that. First of all, let us write what you said. I can say that subset in which no element is sum of two other elements. Great. Is it the same what you said? Can you give me
Yes,
an
ma'am.
example? Can you give me an example?
Ma'am, powers of 3 can be an example.
Powers of 3. So is it sum free or it is not sum free?
Ma'am, it is sum free.
Basically, what he means is that the two or can, okay, let us take in counter example, then I'll explain. What is not sum free? Can you give me an example?
Even
1,
numbers.
2, 3.
Even numbers, okay. Why it is not sum free? Can you tell me?
When we add 2 and 4, we get 6. 4 and 6, 10, and so on.
Yes. Absolutely correct. Basically, we have 2 and 4, we are getting 6, and we are having 4 and 6, then we are getting 10 basically. So I can say that this is not sum free. Okay. Let's proceed in next 10 minutes. Let's take a break and I'll explain about this sum free subset in further detail. So let's take a break of 10 minutes. Let's meet at 6:05. Is it fine?
Okay, ma'am.
Am I audible? Yes, class.
Yes, ma'am.
Yes, ma'am, audible.
Okay, okay. So we were discussing about sum free subset, in which we discussed about like set in which two element is this is this sum of two other elements within that set, as we discussed, like, okay, this is basically the sum free set and this is basically the sum not sum free. Basically, if I say, is this sum free or not sum free?
It is sum free.
Yes, ma'am, some.
Are you sure both, like, it's sum free? Okay.
No, ma'am, it's not.
Which one is not?
Both are not.
Okay. So why both are not?
0 plus 3 is 3, which is present in the subset is in the set, and 1 plus 1 is 2, which is also present in the set.
Absolutely correct. So basically, these both are not sum free. Basically, now coming to the theorem, we'll write the theorem, then we'll try to understand it. This bar is sum free, and can someone tell me what does it mean? Can someone read and try to explain? Try at least. Not the proof, the theorem only. What does it mean?
Ma'am, if we take any set S of non-zero integers and the complement of the set S bar or the subset of the set S, it will have a sum free as you explained above, ma'am, such that two elements will not sum each other, ma'am.
Hmm. What about second? What about this?
For any set of non-negative or non-zero integers, there exists a subset S bar, which is sum free and size greater than and having size greater than n by 3.
Can I say in other words that the size is large?
Yes.
So let's see. Both of you are correct. Absolutely. Let's see its proof. Can someone explain me how it is sum free by giving an example? And is it always sum free or is it not? What I have written.
Always sum free, ma'am.
Are you asking? Can you repeat like you asked?
It is always sum free, ma'am, because k plus 1 and k plus 2, when we add it itself, we are getting 2k plus 3, ma'am. And the maximum element you have given is 2k plus 1, so it is always sum free.
So you are saying that, okay. Okay. Let's check k is equal to 2. Okay. Will 5 come here or not? Can someone tell me? Okay, sorry. Can someone tell me what I have written and is it sum free? You are right that the sum will
Yes,
be
it
2.
is sum free.
Because 3 plus 4, I can't add any of them and they'll lie basically in the set itself. So basically T is always sum free. So let us try to map. I'll write and then we'll explain.
Basically, the sum is at least 2k plus 1. That's why if we add any other number, it will lead to upper bound.
Yes,
It will go out.
yes, absolutely correct. If we'll add 2 numbers, it will go up. That is, as the other person also said, like 2k plus 3, upper bound in there. That will lie outside the set. It will not lie inside the set. Am I correct?
Yes.
So let us take S basically, try to map it to T basically, try to map S to this basically. Now I'll write and then we'll try to understand it. I'll write the whole theorem proof. It's lengthy. And we'll try to understand. I know it's lengthy. First, let me complete. Define random variable. Okay, either we'll try to see bit by bit. So can someone explain me what I have written? Then I'll go to the next part of the proof. Come on. Or let us take a small example to understand what I have written. First try to explain, then we'll take a toy example and try to understand it. Yes, come on. Yes, try at least. Okay, read what I have written and we'll all try to understand. Yes, someone can read. Come on. Come on, come on. Am I audible?
Yes, ma'am.
Yes.
Yes. Can someone explain? Yes.
Ma'am, we are taking a variable S within the range. we are taking a range of numbers from 0 to 3k plus 1, and we are picking a prime number which is 3k plus 2, while k is greater than the s variable which has in its maximum value, and we are mapping that to r dot s mod p. Which this term I don't understand.
Okay, let us take an example and then try to go. Suppose let us take 1, 3, 4. What is max of S?
4.
And now the other step says that pick P, pick prime number P, which is 3k plus 2. Let us take k is equal to 3. So what is prime number? Can someone tell me? Can I say? Now can you tell me what I have written till now?
Ma'am, how you got 11, ma'am?
What is here written?
3k plus 2, ma'am.
Prime number 3k plus 2. Here I have taken, suppose I'm saying that the set is basically 3k is basically the value of k is equal to 3. It is supported. So 3k plus 2, 3 is a 9, 9 plus 2, that is 11, which is greater than max of S. So yes, it is greater than max of S. Now, what is the other thing? R. Let us take a random R basically. And one more thing, it should be co-prime of 11, whatever the prime number. Obviously it will be. So let us take it as basically 2. Let us take 2. I'm just taking the example only. We'll come up with the number, how I'm coming with R and all. That is what we'll do now. Now, as you said, what is R? R into S mod P? Can someone tell me now what will be the set, new set? Now, what will be the new set basically? Come on.
Ma'am, K should be greater than maximum element in S.
K should be greater than max of S. Okay, I thought the prime number should be greater than max of S. Okay, you are correct basically. So can I say it should be greater than 4? So K should be 5, I can say. Is it fine now?
Yes, ma'am.
So 17, I can say. Prime number 17. Can I say?
Yes,
Is
ma'am.
it correct? Now what is R dot now I have taken, suppose R is equal to 2, though we'll come up with that. So 1 into 2 mod P, R into S, basically R S mod P. P is basically 17. Can I say it's 2 itself?
Yes, ma'am.
Now 3 into 2 mod P. Can I say 6? 4 into 2 mod P. Can I say 8? Is it fine? Just I
Yes,
want to say they are trying to say RS mod P, as someone was asking what is this. So nothing, R multiplied by S mod P. So basically now I'll proceed to the next step. Now what is the next step? Now can someone tell me what they were doing? I tried to show with the toy example. Till now what they have done. Can you explain now?
ma'am, we are trying here to map S elements to set 0 to 3k plus 1.
Mm-hmm.
So ma'am, here we are taking a prime number in which ma'am k is greater than maximum of s. So that ma'am, if we take mod, then the mod it comes itself. That is, it is smaller than the prime number.
Obviously, it's
Ma'am,
smaller.
in this way,
Yes, yes.
yes, ma'am. In this way, ma'am, for every element present in set S, if r dot s is equivalent to r dot s bar mod p, ma'am, it is only possible when s and s bar mod p are equal. That ma'am, it makes a one-to-one mapping of s elements to that subset.
Yes, absolutely correct. Basically, it's only possible if S is equal to S bar. Then only they'll be equal, because mod P, whatever we'll do, they'll result in the number itself, because P is much larger. So if I do anything like 5 mod 11, I'll get the number itself. Is it what you want to say?
Yes, ma'am.
So that is what, if it is only possible if S is equal to S bar. So now writing the other part, how we came up with n by 3 and all, let us see. Yes. Any doubts? Okay. I'm writing, then we'll try to understand what is written. Just wait a second. I'll go through each and every line. Now, can someone explain me what I have written? Okay, till that we did okay. S and S bar are basically same, then only it's possible. Now, can someone explain?
Ma'am, we have defined a random variable y, which tells there exists an image and which is present in T also. And ma'am, this gives how many elements of from T does S map to.
So basically, intersection means how many of the elements in T are from which S maps to. Okay, then this is basically tell us how many of them are basically mapping. Then only we'll get as 1. Otherwise, we'll get as 0. Now, what does it mean? Can you explain the whole thing? Come on.
We have calculated the expected value of y by linearity of expectation.
Yes. Yes, absolutely correct. Now we are calculating the expected value of y by linearity of expectation. That is the same. Next. Then so we are mapping like suppose S is equal to 3. Now can you explain? R is equal to, R can be 1 to 10 basically. So R into 3 is equal to, T, suppose 4. and 11 suppose the prime number. So that is how I am calculating R. Is it correct?
Yes.
So I'll calculate the value of R. I have R, I have S, T value and P value. I'm trying to calculate R. Now how I get 1 over P minus 1?
It is the probability of choosing R from P minus 1.
So basically R from P minus 1, that is basically 1 by P minus 1. And then cardinality, as the sum is removed, cardinality of S and cardinality of T. That is what we got. And here, how we get this? What is the cardinality of T?
It is K plus 1.
And how N?
It is the cardinality of set S.
And what is P minus 1?
Our prime number was 3k plus 1. That's why 3k plus 1.
3k plus 2 and P minus 1, that is 3k plus 1. And that is how we got N by 3. That is basically the proof of this. Is it understood? Like what we did is basically we were trying to find the sum-free subset. So basically any set, basically they are not having the sum of the any element there itself. That is basically called as sum-free subset. We saw some examples of that. And then we tried to prove that theorem basically. So we tried to pick up like basically map the S basically to this T, and then we are picking up the prime number the way I have showed the toy example, and then the RS mod P, basically we are trying to find the value, and we also saw that how RS mod P is equal to RS dash mod P if and only if S is equal to S bar, because P is basically having the large value. And then if I say that this is the image and what is the basically the intersection between them, the expectation will be how many number of times they are basically having the common thing, and how I'll find the R, basically that is RS is equal to T mod P, and this is basically the probability and the cardinalities of them, and that is how I came up with N by 3. Should we proceed? Okay. So tomorrow we'll only revise the concepts tomorrow. I hope so. You'll go through the next thing, which is I think only uh, what is discussed in lecture 8. Streaming algorithms will be left. I hope so. Or super concatenators. Let's see. We'll try to complete today the extremal set families. So I hope so you will do yourself. And if you have any doubt, we can discuss tomorrow. Mainly, we'll keep the lecture for the revision. Is it fine, or we should complete these extremal subs? Like we should complete the streaming algorithms, or we should go with the revision and some questions? Yes, what is your feedback? Come on. Class will be 5 to 7 only tomorrow as well. Am I audible?
Yes, ma'am.
So like tomorrow we should revise the and do more problems, or we should go with the streaming algorithms? Yes. Yes, Rupavani. You have raised your hand. You can write in the chat, or you can unmute yourself and suggest something. Any one of you. Yes, Arvind, Preshit, Sobik. Any one of you?
Streaming algorithm, ma'am.
Streaming algorithm. What about others?
Revision is also important.
Okay, so we'll do both of them. I'll just give the gist of the streaming algorithm and we'll mainly focus on revision. Is it fine, both of you?
Yes.
Yes, ma'am.
Okay. So I'll write first. Can someone tell me what I have written and what are unit vectors and okay. First of all, what are unit vectors? Then we'll go to the definition of it. Yes, come on.
And vectors having magnitude 1.
Okay, so is this unit vector? Which one of them is unit vector? One, two, three, four.
Only 1
First
and
and second.
2.
Yes, absolutely correct. Only 1 and 2, basically the other unit vector. Now, can someone read this definition and tell what they are trying to convey?
Given
Come on. Sorry for the disturbance. No.
given n unit vectors, ma'am, there is a binary vector representation, in which sum of bi over n is smaller than root n.
Absolutely correct. So can I say, okay, what is this? What is this symbol? What is the symbol?
For the
The
magnitude.
magnitude. Can I say it's norm? Magnitude is this. Anyone idea about norm? Yes, come on. Yes, yes. It's nothing, only the length of the vector itself, basically norm here. What is the length? Or I can say, as you said, magnitude itself, length of the vector. So basically we have different types of norm, though I'll not go to them. L1 norm, L2 norm. Any idea about Euclidean distance or Euclidean norm? if we write like this, basically that is Euclidean norm. What we do is, like, suppose I have written x and y, and there is an Euclidean norm. So what we do is square. Sorry, something wrong I have written. X square plus y square. This is basically the Euclidean norm. Charging. Okay, and if I say about L1 norm, as it is not written anything, so we'll perceive that it's L1 norm. It's just the addition of the magnitude. Basically, addition of the numbers, basically. That is what we call it as L1. So basically, as you told that in the definition, I just wanted to tell you so that you should be clear that this symbol is basically the norm. And what we are doing is we are doing the linear combinations of the signed linear combinations of the vectors. And these are the binary, basically B is basically binary vector, which is getting multiplied. Yes. Any doubt? B is basically the binary vector, which is getting multiplied by the vector itself, like +1 or -1. And then what we are saying is that the sign, in other words, what we are saying is we're doing the signed sum so that norm is minimized. Or I can say is less than √n. So we are trying to prove this, that how it is less than √n basically. So pick BI. As we saw that obviously it's -1 or +1. We are randomly picking them in IID fashion. What is IID? Yes. What is IID?
Independent and identically distributive.
Yes, we have already discussed in the class. They're independently picked up and identically same distribution is applied. So independent and identically distributed. So now what will be the expected value of a summation of BI? Let's see. So let us say that X is equal to is a random variable. What is X square? Yes, come on. What is X square?
Ma'am, X transpose multiplied by X.
X transpose multiplied by X as it's a vector. So can I say summation of BI transpose multiplied by summation of BI, taking transpose inside. Can you tell me why I haven't written transpose here?
Ma'am, because sigma B is a constant.
It's a scalar, can I say? Basically, if I do the transpose, I'll get the same thing. That is why, in other words. So if suppose they're different, INJ, now what is the value of the expected X square? Expectation, taking on both sides. Now there can be two cases. Either both of them are same or either both of them are different. So let's take one case same and other both are different. Can you tell me what I have done till now? Then I'll go ahead. Come on.
Ma'am, we have taken the value of things as the norm of the sigma into bi into vi, and we have squared the values. And as bi is a scalar value, we have taken it outside, and we have calculated the expectation for the scalar value separately, and then multiplied by the transpose of vl multiplied by vi, then added with uh, s- sum of the expectation of bi and bj multiplied with vj.
So basically we have taken the one case where both are same and one case where both are different. So what should be the answer? Anyone?
Ma'am, can we take in common sigma bi into vl transpose?
Sigma bi into
VL transpose common, and we will get VI plus expectation of BJ into VJ.
I'm not getting your point. So, you are saying can we take bi into vi transpose? This one common here only. We came from here to here only. Not getting your point.
No, ma'am, I made a mistake.
Okay. So can you tell what is the answer of this? Yes. Yes, come on. If it's square, can I say it's 1 only? Because it's plus 1 minus 1, it will be 1 only. And if I say vi transpose vi, they are unit vector, that is also 1. And they are summing up to n. So basically n itself of this. And I can say the expected bi and bj, obviously 1 is plus 1 minus 1. So basically they'll end up in 0 here. The expected bi will end up in 0 here, basically. And that is why we have this 0 here. And we'll end up in n here. And I can say that x square, as we have done, basically it is less than the expected x square basically was n, so x square less than n, or I can say x is less than root n. That is how we got it, that when we'll basically do the linear signed linear combination, we'll end up in less than root n basically. That is what is discrepancy here we are trying to understand. Coming to the next probabilistic method, I'll just go through it. Maybe we'll try to understand it tomorrow, or I'll expect it from you only. Just give the definition and try to understand what it is. Can you explain me? Yes. What is extremal set families? Come on. Yes, come on. Can someone read it and try to understand? Explain, basically. Try to explain. Read it loud. Come on.
Can you explain it? I don't get it.
Hello, am I audible?
Yes, ma'am.
Actually,
Yes,
my
ma'am.
charging is gone. So maybe we'll continue in the next class because I can't share my screen. Can you explain like what is extremal set families at least? Then we'll close this class. Yes, someone was speaking, I think Preshit.
Ma'am, I was saying that it is not clear.
Okay. So basically it is like I can't write. Okay. So we'll maybe understand it in next class only because I have to find the charger and all. Okay, we'll understand. It will take the time to on. So we'll understand in the next class. Try to come up with the example of this extremal set families where we are taking the AI. We are taking the two pairs, like suppose the same pair of the single pair. Basically, they are basically, we are saying that the single pair, they are basically disjoint, and across the pair, they are overlapping. Just a hint. We'll try to understand in the next class what does it mean. I'll try to complete this extremal set family and give you the intuition behind the other things. And then we'll switch up into the, I'll not discuss in detail everything. We'll switch to the revision part because that's essential. I
Ma'am.
think which, and one more, as one of you also said me that previous year question, I'll check that. And one of you asked me about the negative marking. Is it there? I'll also inform you after checking with that. Any other doubts which you want me to discuss?
Ma'am, can you explain the week 2 assignment, ma'am?
We assignments you're saying. Actually, I have already discussed assignments. Maybe I think week 8 and week 7 are left. I've
Ma'am,
discussed.
it is not available in your YouTube, ma'am.
It's available, I think.
Which week, ma'am? Which in recorded video, which week it is available, ma'am?
Every week we are discussing like set of.
Everything. Only 1, 3, 4, 5, 6 only I verified, ma'am. Remaining I didn't get, ma'am. 2 I didn't
Okay.
get. 1,
Okay,
7.
you are able to see the videos week 1 to week 7.
Week 6 only, not 7. Not 7, I think not uploaded. 7 not uploaded, ma'am.
And I have uploaded today only.
Okay. Ma'am, how to prepare for examination? It is enough for assignment question. Otherwise, we will prepare for all the thing.
You can go through all the syllabus, whatever is covered in the class, as well as the assignment questions. And I think we have missed an assignment. I think Preshit was there in every class. Preshit, we have discussed every assignment, or some of the assignments are left. Okay, it's not audible. Maybe. Yes,
Ma'am,
Preshit.
I think most of them were covered.
Yeah, most of them we have covered. You can see in our videos. And week 7 and week 8 are not covered.
I didn't get, I think.
Hmm?
Week 2.
Okay, so we'll discuss tomorrow week 2 if it's left. Week 2, week 7, and week 8 we'll cover tomorrow. Is it fine?
Have the previous year question paper for probability for computer science.
Question paper, I don't think so, but assignments, I can see that if there are previous year assignments. If there are, we can discuss in tomorrow's class the assignment problems only of week 2, 7, 8, and previous year if they are available.
Okay.
Okay.
What will the question pattern in exam?
Actually, I am unaware of it. Maybe I have to check and I'll inform you. Is it given in
Is it
instruction?
similar to, ma'am, is it similar to, ma'am, assignment problems?
I'm sorry, I don't know about this. Maybe I'll check with the other TA or other person who have given this exam, and I'll inform you tomorrow that is it like is
Assignment questions are so tough, ma'am.
okay. We'll discuss it and we'll discuss which part you are getting.
Go through for all the weeks lecture, it is not possible to clear for the examinations.
Hmm?
It is not possible to go through for all the videos. It is not possible to get for clear for the examination. It is so difficult for understanding the all the lectures for week one.
Okay. If you are having any doubt in any of the lecture, you can mail me as well. Like we can. I will be touching the mail. Like I'm sending you the mail ID. If you are not able to understand any problem or anything.
It is only possible for cover for the only assignment question. It is no otherwise it will be go through for all the weeks.
I think you have to go through all the weeks, but assignment questions, obviously, they are important because they are covering all the aspects of the video lectures. Maybe tomorrow I'll come up with the previous year if they are available.
Okay,
I
ma'am.
have written my mail ID also here. You can check that.
I think it's available in your YouTube also. YouTube.
This is in assignment problems, assignment 1, 3, these are available. Previous year or not?
Previous is not available. No, I didn't check week 2 also.
Okay. Week 2 we'll discuss tomorrow. Week 2, 7 and 8. Is it fine?
Okay, ma'am. Better if it is possible to only will we go through for all the week lectures, ma'am. I think it is not possible, ma'am. It is so difficult to prepare for the examination. Only assignment mean it is enough. I think previous year question paper it is available. Will be go through easy, ma'am. Once you can discuss for previous year assignment.
Question paper, I don't think so it's available, but previous year assignments, I'll check once whether it's available or not. If they are available, then we'll go through tomorrow. We'll go through the assignments only. Is it fine?
Okay, sure. Tomorrow
Thank
what
you,
time?
class. Any other comments? Yes.
Tomorrow what time?
5 to 7. I don't know why the mail have not come. I have informed them to take the class. Hope so it should be there. If in case it's not there, then you can mail me regarding that. I'll send you the previous year assignment problem if they are available.
Okay, sure, ma'am.
Most probably class will be there. If it's not there, by in case because the mail has not come yet, though I have informed them, so you can mail me. You all can write the mail ID. I'll surely reply on it.
Okay, ma'am, sure.
Thank you, class. Any other doubts? Thank you so much.
Thank you, ma'am. Thank you so much.
Thank you, ma'am.
Thank you, ma'am.
Thank you.